All right, lecture 24. And as we were discussing, it hit us before class, hit me before class, that we've made it halfway through the semester. Couple of housekeeping items. So I think we're caught up on homework grading. Attendance grades are up to date. The project. The project submittal is being graded. My goal is to have that graded by Monday, and then on Monday I'll just release like the whole project or their submittal too. Everybody, for the most part, everybody's doing pretty well. I don't really see any major issues. I'll say one or two things I think you might find humorous. If you remember, I gave you a very soft, light challenge to see if you could beat my price, and I was just giving the bridges that everybody submitted a spot check. There's a few of you that I think might come close, and 2 or 3 of you that have a chance of beating me. And I'll say this for one of you, in your reasoning as for why you picked one bridge, you mentioned the game Polybridge. And Polybridge. When I think bridge engineering, I think bridges hanging off of hot air balloons. No, but the person that mentioned that, I think they're going to come pretty close. So, but all in all, I was very pleased with the work. So, okay. Today we're going to actually start practicing the principle of virtual work. We're going to be so the way that I have this split up is really the principle of virtual work. If you understood what we were doing with trusses, then what we're doing with beams and frames is basically the same thing, only instead of sums, we have integrals. That's it, okay? What does change is the derivation of the moment functions, at least from a procedural standpoint. And I kind of want to talk about that aspect of it. And that's really what I want to focus our discussion on. I'll get you going, don't worry. So let me pull the slideshow up. And this is, I think, really important for our discussion. So first off, when we're computing the deflection, this is where we left off last time, is that the way that we're going to compute deflection is we're going to use the following expression. And so again, this is very akin to what we were doing for trusses. We were summing up energy terms, only with trusses, we were summing up terms, whereas with beams and frames, we're summing up integrals. Okay? The reason that we were able to sum up terms for trusses is because we can treat the axial forces as constant along the length of the member. We can't do that for moments in beams and frames, so we have to integrate. Okay? Now, we are still going to have to do a real analysis. We are still going to have to do a virtual analysis. And instead of getting a suite of real and virtual values, we're going to get a suite of real and virtual functions. Okay? So the idea is that these big M and little m functions are going to be equations that if I were to graph those equations, that would be the moment diagram. Okay? So basically that's what these big M and little m functions are. They are graphs to plot the shear and moment diagram. That's what they are. Okay? Or sorry, the moment diagram. If we're talking about the shear diagram, we would have big B's and little b's. So right now we're just looking at the moment diagram here. The way that we generate our big M functions is from the real structure. The way that we generate our little m functions is from the virtual structure. Kick all the loads off the structure, place a single unit load at the point of interest with a magnitude of 1 in the direction of the assumed displacement. Okay? We still have our E values. Our I values, we were using areas for trusses. We're going to be using I's for moment of inertia. I think for most practical purposes, it's going to be the same thing in terms, because it's just a section property. It's just a numerical section property, so we can treat it the same way. We do have to account for our unit conversion factors. So for rotations, this is what we left our class with last time. We're going to have to use, for rotations, a conversion factor of 144 times 180 over pi. The 144 resolves the feet to inches conversion, and then the 180 over pi gets our answer in degrees. So when we're looking at structural rotations, the angular rotations that we're talking about are really tiny. And so if you express them in radians, they're like 10 to the negative 3. Like they're really tiny values. So multiplying by 180 over pi gets the answers in degrees, and I think it's a little more, like you can conceive of those answers a little easier. So that's why I throw the 180 over pi in there. Some software packages don't. They just say, here's the answer in radians. So just keep that in mind. And then for deflections, the conversion factor is just 1728, just another 12 on top of the 144. What we're going to have to deal with, and what's going to be the central challenge of beam deflections, is this. Okay, so let's say, for example, I have this beam. Okay, so this is a beam which, by the way, I have got to believe that everybody in here could construct the shear and moment diagram for this beam. Okay, right? Because, you know, compute the reactions and then draw the shear, moment, so on and so forth. The question I want you to ask is how many moment functions, how many m of x functions are necessary to fully construct the moment diagram. So not really from a like from a math perspective, like how many equations, like y equals some function of x, how many of those do we need in order to fully construct the moment diagram? Okay, and there's a really easy way of figuring that out. And the easy way of figuring that out is to imagine a big old section cut and to imagine that cut just moving along the beam. And to keep it really simplistic, whenever you see something different, that necessitates the need for another function. So to give you an example of what I'm talking about, okay, so imagine this is my section cut. So remember, when you cut a section, you can look either to the left or to the right, right? So let's cut a section and let's look to the left, okay? So I'm going to start moving this section cut over. Okay, so if I cut a section and look to the left, what do I see? I see a triangular load, right? I see a triangular load, triangular load, triangular load, triangular load. Bam! Now I see something different, okay? Now what I see is this reaction at B, and I see a distributed load, right? So I keep going, keep going, keep going. Is there anything different between like here and here? It's still a triangular load, distributed load, reaction, right? Over here, triangular load, distributed load, reaction. It's not until I get here that now I start seeing something different. I see a new reaction, new triangular load, and so on and so forth. So if we were fully defining this moment diagram, how many moment functions would we need for this moment diagram? Three. We would need 3, right? So, for example, at a minimum, and this will become more of a topic of, later, but if we say that the origin is like right here, so what we might have is, if we're computing some deflection, we might say we'll have an integral from, 0 to 12 of, some stuff dx plus an integral from 12 to what? So this is 0 to 12, and this is going to be 12 to what? 32, and then 32 to 38. So at a minimum, we're going to have, something like this. 20, sorry, that's 32. Right? So that's at a minimum. We might end up actually having more, but we'll get to that later. Like we're going to start off with dealing with problems where we're only going to have one integral, and then we're going to step up to problems where we would have more. So we'll keep it simple to start. And then the other thing that we might have to do is we might have to take this whole thing and multiply it maybe, I don't know, by 1728 over EI, right? We got to throw our EI in there because EI is on the bottom, and then we'll have to multiply it by 1728 to get our units correct. Does that make sense? So again, I'm just giving you kind of a general idea, and then we'll expand upon this later. Like I said, we're going to start simple. Don't worry, we're going to start simple. Okay? Now, I want to look at the virtual loads. I want to look at that. So let's take a step back. Okay. So we're going to be doing at a minimum 2 analyses. We're going to be doing a real analysis, and we're going to be doing a virtual analysis. Right? Okay. So let's think about this. The virtual analysis is kicking all the loads off the structure and replacing it with one load. And the one load is either going to be a concentrated force or a concentrated moment, right? So let's take a look at what the shear and moment diagrams look like. So here's what the shear and moment diagram looks like for a concentrated load, right? We have constant shear, linear moment, right? Okay, and then for a concentrated moment, we have constant shear, we have constant moment. Like the moment doesn't affect the shear diagram, and as for the moment diagram, it would just be this, right? So the real point I want to make is, does anybody see any pattern with these moment diagrams? So if I have a structure that has nothing on it but either this or this, does anybody notice something about the moment diagrams? And the answer should be, they're all linear. They're all lines, right? Okay, are you with me on that? So what I'm getting at, here's what I'm getting at, is if we're talking about virtual functions, because the structure is only subjected to one concentrated effect, they're always going to be lines, okay? And the value there is that you can always find the equation of a line a lot easier maybe than cutting a section. Remember, we can always cut a section to determine a moment, right? Well, we could also just plot the moment diagram and just look at our values. For example, like I said, we could cut the section, but that could be tedious. Here's something else that we could use. That's just basic geometry. For example, how do we find the slope of a line? The change in y over the change in x. But by the way, do we even need to worry about finding the slope of a moment diagram? Because isn't the slope of the moment diagram just the shear, right? And then we could say y minus y1 equals m times x minus x1. Use point slope formula just to find the equation of a line. Isn't that a lot faster than cutting sections? So for your virtual functions, it might be a lot faster to find the functions this way than it is cutting a bunch of sections. Okay, and I'm throwing this out there because I'm trying to make your life easier and faster when doing these problems. Okay, 6.2, homework 6.2 is going to be kind of tedious. And I'm throwing this stuff out at you to make your life easier when you do that assignment. Okay? So far, so good? And I'll demonstrate what I mean here in a bit. Okay? And by the way, I should mention that if you ever have a linear real moment diagram, this would work too, that you could just use point slope formula to figure out your function. Don't worry, I'll show you how that works in some examples. Okay. Everybody good? Okay, this is going to be our problem for today. Let me go to the notebook here. All right, so, oh, that wrong one. We're on example 1. Okay, so here's our problem, and I want to find the vertical displacement and the rotation at point A. Okay, I want to see what is going on with this point here in terms of displacement and rotation, okay? So the idea, just to maybe, I don't know, put a little picture up here, is here's the beam, backwards. And if the beam is subjected to some load, I propose, so imagine you were holding like a flexible ruler in your hand and you just applied some force over it, okay? I propose that the ruler, or the beam in this case, is going to deflect something like that, right? Okay? So not only are we going to get, here, let me do this. Not only are we going to get some displacement, but we are also going to get an angle change, right? So it's not only displacing, but that point is rotating, okay? So let me see if I can clean that up a little bit. So we're going to get an angle change, and we're going to get a displacement. And our goal in this is to see if we can develop values for both of them, okay? That's what our goal is. We're going to see if we can do both, okay? So a couple things that I'm just going to make sure that we all have in the back of our head. So So I'll say this. I'll say our deflection or our rotation is going to be summing up all of our integrals of dx. And then the other thing that I'll just make sure that we're aware of is our unit conversions. So our unit conversion for rotation is 144 times 180 over pi, and our unit conversion for displacement is 1728. And don't worry, we'll see how these are applied here in a bit. Okay. Everybody kind of get a general idea of what we're doing here? Okay. All right. So the first thing that we're going to do is we're going to look at the real moment functions. Okay. So keep in mind our goal is to look at these integrals. Okay. Now let me go back to our section cut example. How many functions are we going to need to fully define the moment diagram for this beam? How many? One, right? I mean, what does the moment diagram look like for this beam? I mean, let's just sort of conceptualize that. What is the moment diagram going to look like? I mean, we don't need the values to sort of get the idea. So the shear diagram is going to sort of like go down, and then there's going to be a reaction that brings it back up, right? And then the moment diagram is going to sort of do like that, and then there's going to be a reaction that brings it back up. So we're going to have some moment diagram, which is a parabola, right? Is that right? Okay. And we only need one of them because it's only one equation to fully define the moment diagram, right? So what I'm going to do is this. I'm going to cut a section. Okay, I'm going to cut a section. And which direction do you think I should look? To the left or to the right? Left, right? There's less going on. So here's an interesting question. Do I even need to calculate the support reactions to get this moment function? No, because it doesn't matter, right? If I wanted to fully construct some shear and moment diagrams, it probably didn't hurt, but I don't really need it for this problem. So I'm just not going to worry about it. So what we're going to do is we're going to say, okay, real moment function okay, so I'm going to cut a section and I'm going to look left. All right, so what does that look like? Oh, sorry. So let's see, I've got this beam cut right here. I've got a load right here. This is 2.5 kips per foot. Okay. We're cutting a section because we're trying to derive a function, an equation as a function of x. So the distance from the left support is going to be some distance x. Okay? So tell me what to do. How do I collapse this point load? What's the point load going to collapse to? What's that? Well, that's how far away it is from the section cut. How much is it? 2.5x. And what we're interested in, we have our shear and we have our moment. What we're really interested in this case is the moment. We don't really care about the shear function because we're defining our deflection as this. And by the way, near the end of our talk on this, we are going to take a look at what would happen if you consider shear. That's a later discussion. We'll get to that here in a bit. All right, so I'm going to cut a section, I'm going to sum moments at the section cut. I already cut the section. Okay, so tell me what to write. How do I account for this? What do I do? Does it go on left or right?
2.5x times x over 2 is going on the right side.
There you go. 2.5x times x over 2. And then, is there anything else I need to put in this table? M, and that goes on the right. Okay, so 2.5x times x over 2 is 1.25x squared, right? Okay, so let me show you how I'm going to write this, okay? And I want to get into this habit, okay? So therefore, what I'm going to say is that m equals minus 1.25x squared, okay? But what I'm going to do is, the beam is how long? 15 feet long? Yeah. Okay? So what I'm going to do is I'm going to say that this is from 0 to 15, okay? Okay? Now, do we have a simple way of checking as to whether or not this is in fact correct? I would think so. We can just plot this in Excel, right? I kind of need my keyboard to do that. Let me grab this over here. So let's just see what would happen if we plot this. Okay. And I'm going to do a real quick and quick plot here just to see what happens. All right. So how long is the beam? 15 feet. $1.25? Is that what we said? Does that look right? That looks right, doesn't it? So we have a simple way of just checking whether or not the function that we've derived makes sense. Okay, so that is always going to be advantageous, or that's always going to be available to you. Okay, so let's write this down here. So we have m of x. Sometimes I skip the of x and I just write m, but if you want me to write that, I will. It is negative 1.25 x squared, valid from 0 to 15. Now this valid from 0 to 15 is not really going to matter for this problem, but it will matter for later problems because we'll have multiple functions. So I want to get in the habit of sort of describing that. Okay. So far so good? Okay. So now let's do a virtual moment function. Okay? So virtual moment function. Now, this problem, okay, this problem is asking for two deflections, or two things we have to evaluate. We have to evaluate the displacement at A, we have to evaluate the rotation at A, okay? So what I'm going to do is I'm going to say virtual moment function for displacement at A. Okay? All right. So let's see how we would do that. Okay. So how did we do virtual analyses for trusses? We take the structure. Okay. So let's see. Here's the structure. This is the structure. That's point A. We kick all of the original loads off the structure. Get all the loads off the structure. Kick them off. And we replace them with a single unit load at A. Now, for the original structure, do we all agree that a reasonable assumption would be that point A deflects downward? So here's what I'm going to do. I'm going to place a single unit load right there. Okay? With me so far? Now, by the way, let's just sort of conceptualize this. What do we think the shear diagram and the moment diagrams look like? Let's do V and M. So we're going to have down, over, up, right? So the shear diagram is going to be down, over, up. Like that's what it's going to look like. So what's the moment diagram going to look like? It's going to go down, up, right? Everybody good on that? Okay, so we'll see if that's right. Okay, so what I'm going to do, cut a section, look left. I'm going to look the same way I looked before. So we'll say little v, little m, that x. Okay. Tell me what to write. How do we handle this? What's the moment at the cut from that?
1 times x.
1 times x, which side, left or right?
Right.
Right, so we have 1 times x. And a lot of times I will write my 1 as 1.0 just so it's sort of like not mistaken as L or I or something like that. So that's just me trying to make sure that you all can read my handwriting. Then we have the m, right? And the m goes like that, right? So 0 equals m plus x, right? Everybody with me on that? So would you agree that m is going to equal minus x? And that's also going to be valid from 0 to 15, right? So, okay, what I might do for the purposes of notation is I might call that m delta because I'm going to have another little m function for rotation. So that's just me sort of differentiating what I'm about to show you here in a second. Okay, and again, can we validate this? Well, absolutely. You know, just go here and say do that, and then does that look right? Looks right to me, you know. So that one's a pretty simple one to just sort of know that it looks right. But later on, some of these functions may not look so simple, and so being able to graph them is pretty important. Okay, so we'll write little m, and I'll just put m delta is minus x. Also valid from 0 to 15. Okay. So far, so good? So now let's do the method of virtual work, okay? We'll evaluate this deflection, then we'll come back and do rotation. So what we're doing here is we're saying that the deflection is the sum of the little m over EI dx integrals. That's what we're doing. But we only have one integral to evaluate. Again, this problem, we're only going to have single moment functions. This homework, only single moment functions, but later on we might have multiple ones. Okay. All right, so let's sort of write down all these terms. So we have an m of minus x and m of minus 1.25 x squared. By the way, if we want to throw some units on this, so this would be foot kips, okay? And for those of you that are wanting to be hyper specific about your units, the units for this is actually feet, okay? Because you're taking a moment is a force times a distance. The force is unitless, so it's a unitless force times a distance. That's why it's feet. Okay, E. What was E in the beginning of the problem? What was it given as? 20,000. That's 20,000, and that was in KSI. And we were given a moment of inertia of 1,500. And if you recall, moments of inertia are in inches to the fourth. So it's like an area times a distance squared. So that's why it's inches to the fourth. Okay. So what I'm going to do is a little bit of algebra off to the side. So the first thing I'll do is I'll do that, little m times big M. So that's going to be minus x times minus 1.25 x squared. And so little m big M is 1.25 x to the third, right? Okay. And maybe what we'll do is also formalize that and say that that is valid from 0 to 15. Okay? So therefore, the integral is actually pretty easy. So if I want to find the deflection at A, remember, the deflection is just summing up all of that internal energy. Okay? So what I'm going to do is, this is how I'm going to do this. I'm going to integrate. So what we're going to do, we're going to integrate from our little m big M over EI. Okay? Or here, let me get formal. Let's move that over here and say we're summing these up. So here's how I'm going to do this. Okay? We're going to integrate from x equals 0 to x equals 15. Okay? Of the following. Okay? So what is little m big M? Little m big M is 1.25 x to the third, right? And then EI, E is 20,000, 1,500 dx. Okay? Now, did I forget something? For the astute observers? The unit conversion. What I will do is take this entire integral and multiply it by what? 1728. And the reason we're multiplying it by 1728 is because KSI in inches to the fourth for our denominator terms, but our numerator terms are in feet. Okay? And so we've got to resolve that. We end up having 3 feet terms that need to get converted to inches. Okay. Now here's the thing about this integral. And I know that, it's 10 o'clock in the morning and you're thinking calculus, it's too early. But I really want you to take a look at this integral because it's really not hard. Okay? First off, I seem to remember this rule in calculus that says that I can factor out constants. Right? And then what am I left with? An integral from 0 to 15 of that. I mean, isn't that pretty easy? Now, here's the thing. Let's talk about this. I want to be clear that this is not a calculus class, okay? So, you all need to be able to perform integrals, but when I say the integrals are simple, I mean it, okay? This is about the most challenging integral that we will do in here. It's integrals of polynomials, okay? So, I mean, first off, I'm just going to tell you that the answer to this integral is 12,656.25. Okay? Now, just to be clear, if we want, we could say that the integral from 0 to 15 of x to the third dx is x to the fourth over 4, evaluated from 0 to 15. So factor out the 1/4, 15 to the 4 minus 0 to the 4, which is 15 to the fourth over 4. Okay, and plug and chug, that's what you're going to get. Okay, so I don't want you to think that like I'm shying away from doing the calculus. I'm happy to go through it. Okay, but I think my real point that I want to make with this is that we're going to start getting to the point in some of these examples where I get to a place like this and I just say, here's the answer. And I've got to believe that you all can do this. By the way, if you have a Casio FX115 ES Plus or similar scientific calculator, it will just do this for you. Okay, like this is a very basic definite integral, and any scientific calculator worth its salt will do this integral for you right now. Okay, and I encourage you to do that on an exam. I don't have a problem with that. Okay, that's not an issue. Okay, sound good? So the deflection would then be 1.25, 1728. 12,656.25 over 20,000 times 1,500. And when you evaluate that, what do you get? And typically, I tend to ask that deflections get reported to 3 decimal places. That's sort of a standard in most software packages. Like most software packages will do 2 to 3 decimal places, no more.
0.911.
0. Now, so it's 0.911, but positive 0.911. Okay. Do I have a second on that? So what does that mean? I propose that the deflection at A is 0.911. What are the units for that displacement? No. Inches. Like when we developed our conversion factor, we developed it to achieve a target unit system of inches. And that's the magnitude. The direction is downward because we got a positive answer because that was our assumption. Okay? Now we're not done because we got a rotation to do. But let's just take a step back. Is that too bad? Everybody okay with this? Y'all good? Back, everybody good? Okay. So, the next thing to do, if we want to close this out, is the problem asked us to compute both the displacement and the rotation. Okay? So let's talk about how we would do rotation. Okay? So if we sort of scroll through the problem, we said, okay, we have a real moment function, and then we had a virtual moment function for a displacement at A. Really now what we're going to need is we're going to need a virtual moment function for the rotation at A. Okay, we're going to need that. So we're going to do another virtual analysis. Okay. Okay. So let's see if we can develop a virtual structure in that regards. So here's our beam. This is point A. And remind me, let's see. we said that the beam is going to deflect, I don't know, something like that. So what you're telling me is that it used to look like this, and now it looks like that if we're looking right there. So the rotation goes like that. So maybe what I ought to do, place a unit moment like that. And by the way, like if you're getting worked up over whether or not it needs to rotate this way or this way, it doesn't matter, just guess one, okay? And if you get a negative answer, it's just going the other way. That's all that means. Make sense? Okay. So, same thing as before, right? So we'll say what I will say that ends up becoming, it's not really an issue for this problem or the homework assignment that you're about to do, but what does become an issue is ensuring that the moment functions all respect the same coordinate system. So at least for now, until we dig into this with more detail, if you look left for a real moment function, probably a good idea to look left for a virtual moment function. Look the same way, okay? You don't have to, but I'll talk later about what happens if you do, and you'll get the same answer, but the algebra tends to get pretty messy. You'll see what I mean. So, all right, so okay, so there's our function, or there's our section cut, right? Just looking at this part over here. So if I sum moments at the cut, what do I do with this right here? What do I do with it? Do I put it here at all?
On the left.
It goes on the left,
On the right.
on the right. So I put 1 times what? Hold on. It's a moment.
Yeah, it's just one.
This is a good thing. Remember, we don't multiply it by a distance at all. It is a moment. We are summing moments. Just put 1, okay? So therefore, bless you, our m theta is going to be -1. Valid from 0 to 15. So typically, if you have this and this, usually you're going down in order, right? So this is an x term, this is a constant term, typically. Not always, but typically. Everybody good? So the method of virtual work then is pretty easy, right? So this is -1, and the units for this are actually unitless. We still have our same real moment function. That doesn't change. We have our E value, 20,000, not 29. Here, I'll do the same notation. Okay, so a couple things that we can do, just like with last time, we'll say, okay, let's do this algebra first. So we'll do 1.25x, why did I say x cubed, it's x squared. I think I'm getting ahead of myself. Okay, so now we can now compute our rotation, right? We're still going to use the same idea. We're still going to sum integrals. But we're only going to have one integral, okay? And it's going to be an integral from x equals 0 to x equals 15 of a big old fraction. The EI on the bottom. On the top, we have that. And then what's our unit conversion going to be here?
Times
144, 180 over pi. And again, this is pretty easy, right? Because everything that's a constant just gets factored out, right? So if I factor everything out that's a constant, I'll stick that all over here on the left. So I've got one big old fraction, 1.25, 144, 180, 20,000, 1,500, and pi. And what am I left with? I'm left with an integral from 0 to 15 of x squared dx. I mean, that's pretty easy, isn't it? So are you okay if I just tell you that the answer to that is 1125? And what do we get here? We'll say also maybe 3 decimal places. Positive, by the way. Anybody got an answer? 0.387?
Yes.
Okay, so therefore, the rotation at A equals, so let's 0.387. What are the units for that 0.387? Degrees. And in which direction? Well, which direction was our concentrated moment? What is that, counterclockwise? So, counterclockwise. Not too bad, right? So I will let you know that for your assignment due Friday, I did, well, I made it a little on the challenging side. I should go ahead and let you know. So here's what I did. So for your homework assignment, what I did is I made it a triangular load. And what I am doing for this problem is I am asking you to work a little backwards. I'm asking you, what does the I value need to be? What does the moment of inertia need to be such that the deflection is a certain value? Okay. which is very much a design problem, right? Pick a beam such that it won't deflect too much, okay? So the cutting a section, keep in mind we've cut sections with triangular loads before, so refer to a lot of that we've done before, but yeah. That's all I got, everybody. I'll pull the code up one more time.